in reality, it probably looks a little bit more like this. But I think it's good enough for full credit if you drew it like I did initially. I think it's good enough for full credit. There's your velocity vector. I can, I think, also ask you to add the acceleration vector to the picture now. The acceleration vector is the derivative of the velocity vector, which again you could write. I won't mark it wrong if you write it as a point, but you can also write it with I hat and j hat. Differentiate this now. The derivative of the I hat is 0. It goes away. The derivative of 3/2 t to the 1/2 j hat would be 3/4 t to the negative 1/2 times j hat. The j hat just stays there. So at time 4, a of 4 is 4 to the negative 1/2 is 1/2 times 3/4 is 3/8 j hat. The velocity vector, or the acceleration vector, points straight up with a length of 3/8. It's pretty small. It's a pretty small acceleration vector. The angle between the velocity vector and the acceleration vector is less than 90 degrees, so the object is speeding up. If you graph the speed versus time, graph this versus time is going to look about like that, I think. That's going to be the speed versus time. It is speeding up. That angle is less than 90 degrees. The green vector is tending to get longer here as time goes by. The distance traveled is this. I said to use a substitution to find the distance traveled as a function and change your limits of integration appropriately. I do remember people had trouble with that part too. How are we doing for time? Not much time. This is only exam 1. Let's just get you started on this. Maybe I need to make another video later this afternoon. Add more review stuff in. You won't have to attend it though. I think I probably should try to make another video. If I can find something to actually videotape for me. You let W equal 1 plus 9/4 tau. Tau would be your dummy variable. dW would be 9/4 d tau. And when you do the substitution, you need to change the limits of integration. You're going to get a W to the 1/2 and a 4/9 dW if you solve this equation for d tau. When tau is 0, W is 1. When tau is t, W is 1 plus 9/4 t. So this is the integral you end up doing with those limits of integration. Your answer ends up involving a 3/2 power, and ultimately involving t, because that upper limit involves a t. At the end, I'll let you finish that. Here we are, volumeless revolution. Quickly talk about that. So we're revolving a region between y equals 1 and y equals x squared, between 1 and 5 around the x-axis. Remember, for those, that you need to slice the region with your pretend knife and look at the cross sections. They are washers or annuli. Rings are the 3 words we use for those. You need to find the area of the outer disk minus the area of the inner disk using those 2 radii to help you find the cross-sectional area as a function of x. And those radii are going to be related to these equations. And then you're going to get a pi involved as well. You need to integrate the cross-sectional area function from 1 to 5. as a real quick summary of what to do. Some examples in the book, you can look those up. It's not too hard, but you know sometimes people have trouble with it. I think this one's a little trickier. Find the volume of a solid over region whose cross-section is perpendicular to the x-axis or semicircle. Semicircles, I do think people have a little trouble with this. It is helpful to try to draw it, a three-dimensional picture. Maybe with an XY plane going into your paper like that. And like a vertical axis that you could label Z if you like, going like that. This region, x goes between 0 and 2, and y goes between 0 and x squared. In this picture with perspective is a region that looks about like this. That curve is y equals x squared, and this is x equals 2, there, that line. And you're doing cross-sections perpendicular to the x-axis, and you're saying they're semicircles. So for any given x between 0 and 2, you want to draw a semicircle on top of that. I made it a semicircle. On this exam, I could make it a square, or maybe an equilateral triangle for you guys on the final exam, or for a future class. But here there's semicircles. The solid looks like this. Sort of like a horn. The principle, though, is the volume is the integral of the cross-sectional area. You find the cross-sectional area at an arbitrary x as a function of x, and that's the function you integrate. We justified that intuitively in terms of slicing and using Riemann sums and or infinitesimal approaches. But that's the gist of what you end up doing. Is once you find that A of x, how do the area of the semicircles depend on x? Then you integrate that function. You know, these things are going to be relevant. A of x is going to be related to x because of this expression. That typically is pretty tricky for people, so that's definitely something to practice. Here you've got a thin rod. The mass is just the integral of the density. It's a thin rod. We don't need to worry about a two-dimensional thing here. Location of the center of mass. Once you have the mass, you also have to find the moment. Integrate x dx to find the moment and divide by the mass. That'll give you the center of mass. The thing at the top is called the moment. You may recall. Maybe I would like to not have to make another video. Are you okay with going a little late here? You have a class? Or, okay, well, you guys can leave then, and maybe I'll continue making this video a little bit, and you can watch the last 5-10 minutes or so. Is that okay? We still have a couple minutes. This was a probability problem, not actuarial stuff, just plain probability. We've got a PDF. Remember that you integrate PDFs to find probabilities, and in part A we're finding the CDF. You've got to find an antiderivative of the PDF, but it's not just any old antiderivative. It's graph for these kinds of variables that start at a value of 0, has to go through the origin. So you find a particular antiderivative that goes to the origin. I think it's going to look like this for the graph of capital F. Yeah, it has to. And it has to approach 1. Integrate little f and find that particular antiderivative to find capital F. You can use capital F to find the probability in part B because of the fundamental theorem of calculus. You integrate little f to find the probability, but you've got capital F, you've got the antiderivative from part A. You can just do a difference to calculate the probability. Capital F of 5 minus capital F of 3. The mean wait time. For the mean, you need to integrate x times little f. It's analogous to a moment. In this case, from 0 to infinity. It would be an improper integral. And the median, you set the CDF equal to 1 and solve that algebra equation for t. Guess I'm mostly just telling you what to do here, it seems. I think with the true-false, I'm going to let you think about it. Actually, I wrote down the answers. I circled the answers on your exam too. I might change the wording here a little bit if I give you problems like this. So a true question could become a false question, though not necessarily a question.
I was just going to say maybe you could just put together review top of the second exam for the second section, and then maybe watch that, and then review for the first exam.
Okay. I guess I'll need somebody to videotape the second section, but I think I can do that. Let's go ahead and class that, okay?